Beneath our skin, the pulse of life beats in a continuous rhythm, driven by the heart, nature's most powerful engine. From ancient doctors feeling the pulse with 3 fingers to the first experiments on horses, humanity has long sought to measure this force. Finally, the 19th century brought the silver columns of mercury. Physicians once relied on stethoscopes to catch the faint Korotkov sounds as mercury rose and fell. Mechanical gauges flickered with every heartbeat, requiring focus and precision. This complex dance of hand-pumped bulbs and synchronized listening made measuring blood pressure a delicate art that only a trained expert could perform. By the 1970s, early electronics began to replace manual methods. The oscillometric technique was born, allowing machines to sense the vibrations of our blood. From bulky desktop units to the compact handheld devices of today, we have transformed a clinical procedure into a simple, life-saving task anyone can do at home. Large LCD screens have replaced toxic mercury, glowing softly to provide clear results even in the dark. Accuracy is no longer dependent on a doctor's hearing, but on digital precision. 3D designs reveal the complex world inside, a harmony of plastic, circuit boards, and air pumps, all working together to protect your health. We enter the sterile world of the cleanroom, where technicians pass through air showers into a realm of silence and light. Here, robotic arms move faster than the eye can see, assembling the delicate components of a modern home doctor. This is the birthplace of reliability, where technology meets the heartbeat of the world. Green circuit boards wait for their digital souls. After solder paste is applied, a tiny MEMS pressure sensor, no larger than a grain of rice, is placed at the center. This is the heart of the machine, the vital component that determines every reading. Without this microscopic miracle, the bridge to accuracy would not exist. High-speed robots fire capacitors and microcontrollers onto the board, creating the brain that will calculate complex algorithms. As the boards pass through REFLOW ovens, the solder melts and locks every component into place. Automated optical systems then scan the joints with lasers, ensuring every connection is perfect and strong. On the computer screen, green lights confirm a job well done. Nearby, LCD screens are laser cut and fitted with flexible cables through intense heat. Every number flashes to life in a test of pure clarity before the screen is united with its motherboard. This is where digital logic meets a visual interface for the user. A backlight is added for nighttime visibility, followed by a protective coating that shields the circuit from moisture. Pure ABS resin is fed into massive injection molders to create the machine's outer shell. As the warm plastic emerges from the molds, it carries the sleek, ergonomic shape of a modern medical instrument. Technicians trim away excess resin, ensuring every edge is soft and safe to the touch. Labels are silk-screened onto the surface, marking the vital signs of systolic and diastolic pressure. After the ink is dried, rubber buttons are fitted into the front panel, providing a satisfying tactile response for the user to start their day. Protective glass is sealed over the screen, and the motherboard is secured within the plastic housing. Every screw is driven home, finalizing the marriage between mechanical strength and electronic intelligence. This perfect combination forms the body of the device, ready to be fitted with the lungs that will drive the air. Battery contacts are installed and soldered to the main board, while leakage tests ensure the energy will last for months. The half-finished units wait in a silent line for their air systems. We now move to the area where the mechanical breath of the machine is born, focusing on the pumps that will soon squeeze the arm. Tiny copper coils are wound into mini motors, where elastic rubber diaphragms are fitted to create the pump. Once the metal casing is sealed and lubricated, the pump is tested for its quiet, smooth flow. Nearby, solenoid valves are assembled with precision springs, the gatekeepers that will control the release of every breath. The valve's timing is critical, determining exactly how fast the air escapes. Once verified, the pump and valve are integrated into the main body. Soft silicone tubes are connected and secured with metal clips, forming a secure network that links the mechanical lungs directly to the digital heart of the pressure sensor. The cuff begins as waterproof nylon fabric is cut by high-power lasers into perfect standard shapes. The internal air bladders are made from soft, flexible PVC and sealed through high-frequency heat welding. We inflate these bladders to their absolute limit in a brutal test of strength, ensuring they will never burst under pressure. Once inserted into their nylon shells, the cuffs are sewn together by high-speed industrial machines. Heavy-duty Velcro is added, providing that signature sound of security as it is tested for its grip. Long air tubes are then fitted with plastic connectors, completing the bridge between the human arm and the digital machine. Instructional graphics are printed onto the fabric, guiding the user to a perfect fit every time. After biological tests ensure the material is safe for the skin, the finished cuffs are gathered. We return to the main assembly line where the final back cover is closed and secured with 4 corner screws sealing the technology. Rubber feet are applied to hide the screws and prevent the device from slipping on a table. The blood pressure monitor has finally taken its complete form. It is no longer just a collection of plastic and wire, but a finished medical tool. It is now ready for the most important phase of all, the pursuit of absolute accuracy. We enter the soul of the process, calibration. Each machine is connected to a blood pressure simulator that creates perfect artificial pulse beats. Technicians compare the machine's readings against an absolute standard, while software automatically adjusts the sensor's logic to 0, ensuring a lifetime of medical trust. Static pressure is held at 300 millimeters of mercury to check for the smallest air leak. The quick-release valve is tested to ensure a rapid and safe exhaust. The machines are then placed in climate chambers where they must perform perfectly at 5 degrees and 40 degrees, proving they can survive any environment. Robotic fingers press the buttons 10,000 times to test their lifespan before the device is dropped from 1 meter onto a wooden floor. After the fall, the screen must still glow with perfect clarity. A real cuff is attached for one final test, as the pump hums softly and the numbers climb steadily up the screen. A green light signals a healthy result as the final QC seals are applied to the screws. Every device receives its own unique serial number, a digital identity for its journey. The machines are nestled into protective trays alongside their cuffs and high-quality batteries, marking the final stage of their journey in our factory. Manuals and warranty cards are placed on top before the vibrant carton is sealed by a robotic arm. These boxes are weighed to ensure every accessory is present and accounted for. Finally, the pallets are wrapped in protective film, ready to carry our promise of health and accuracy to homes and families across the globe. In a warm living room, a woman relaxes as the cuff inflates. The result is clear, with smart indicators even warning of irregular heartbeats. Through Bluetooth, the history is sent to a smartphone, creating a monthly health map. Doctors can now monitor their patients from a distance, watching over every beat with total confidence. A gift of health from one generation to the next. Looking ahead, future technology will monitor our hearts without any inflation at all. As we look over our modern factory, our mission remains clear: understanding the heart, protecting the rhythm of life. Because every heartbeat matters, and every life is worth the precision.